So in the last class, we have seen arc welding, right? Arc welding was what we saw. This type of welding, that is submerged arc welding, right, is basically a type of arc welding, we can say. But with the specific, as you can see, it is submerged arc welding. So a little difference here, but it will make a lot of difference actually in the product that we get. The process is a little bit different. You have an arc, but that arc is submerged. Let's see what that means. Okay, so you see, this is a type of arc welding process. That's the first step, right? That we can understand by the name. Discovered in 1935 by Jones, Kennedy, and Rutherford. This welding is defined as a joining of metals with the application of heat and also granular flux, right? That's what differentiates it from simple arc welding. That you have the application of heat, which was there in arc welding, but you also have granular flux here, right? This flux is not the same as your electrode flux, okay? That you had the coated electrode, right? This one is a bit different. So we'll see what how this granular flux makes it different. The submerged arc welding. We'll see. Welding process used in long pipe welding, electrical poles, and turbines, etc. Okay, these are general applications of submerged arc welding. So you see the setup parts or equipment for submerged arc welding. You have the consumable electrode, right? The electrode will be consumed in the as the weld takes place, right? In the weld pass. You have a power source, granular flux, base metal, right, which is to be welded, and the electrode holder, right? These are the main parts, setup parts, we can say, of submerged arc welding. So as the name suggests, the consumable electrode is the electrode which is having current, right? The current will pass through that electrode, and when it is touching the workpiece, it gets melt there. So as we have seen in arc welding, right, the same principle, how the arc is generated, because the current passes from the electrode, it tries to pass from the electrode to the workpiece, right? But because there is some gap between the electrode and the workpiece, that resistance generates heat, and that heat is responsible for melting the base metal, both the base metal and the electrode, right? So that the electrode gets deposited onto the base metal, which is to be joined, right? That's what we have read in arc welding. So similarly here also, same process, right? It is consumable in the sense it gets melted and deposited onto the gap between the two metals to be joined, right? So another thing is power source, right? For the operation of welding, power is required, right? A good amount of heat we require, right? That heat is what is responsible. I'm sorry, the heat is generated because of the current. In that current is where I mean the power source is responsible for generating that current, right? So that the workpiece and the electrode can melt easily, right? Granular flux. You see, the main function of granular flux is to avoid the exceeding heat which is generated when the electrodes touch to the workpiece, right? So to avoid the excessive heat, right? Trying to stabilize the heat, we can say, right? Base metal is the metal on which we have to weld it, right? Very simple. Common metals which are welded with this kind of with this type of welding is carbon steels, right? Especially for structural and vessel constructions, right? We have those big structures and vessels, right? Pressure vessels in the oil and gas industry, or even food industry or pharma, etc. Low alloy steels, stainless steels, nickel-based alloys, right? These are the general metals which are welded. Electrode holder, as the name suggests, holds the electrode, and it is a non-conductor device, right? Because the welder will be holding this electrode holder, so it has to be an insulator type or a non-conductor device, right? It shouldn't conduct electricity. electrode holder. You see here, this gives you an idea of the working process of submerged arc welding. So what is happening is, as we are going, you see your travel direction is to the left. So as we are going from right to the left, right, the weld is being performed from the right to the left. So this is where the weld is already done, right? Here it is taking place. You see, you have a granular flux here from the hopper, right? This is where the granular flux is fed in, right? Here is your consumable electrode. So what is happening is, as the electrode moves, right, this granular flux is laid, right? The path is laid with the granular flux, right? And this electrode, it does its work, right? Just as we have learned in arc welding, it tries to create an arc, melts the this metal, base metal, right? It also melts the granular flux, right? Because you have laid this path, right? You filled this path with granular flux. So you see a blanket of granular flux. So that some of the granular flux would be staying on top of this weld metal, right? It will not melt. Not all of this granular flux will melt, right? The one which melts and joins with the weld metal, it is mixed with the weld metal, right? The one which is not joined, it stays on top of this weld metal, right? Basically, it tries to uh, reduce the solidification time, or the loss of heat, right, is also reduced, right, because of the granular flux. It tries to have a coating, and therefore it reduces the solidification, or the heat, what do you call, the cooling time, right? It increases the uh, cooling time, the time required to bring the weld area to the room temperature is reduced because of the granular flux, which is not melted. As you can see, the blanket of granular flux, right? And you have this vacuum system for recovery of granular flux. That which is not deposited onto the weld metal, nor it is melted, it has to be taken with the help of this vacuum system, right? That's what is happening. And on the top, you have, on the top of this weld metal, you have the slag, right, which is solidified flux. As I've said, you have just on top of this weld metal, this granular flux, right, because of the heat of the weld metal, it will stick to the weld metal, right? So that is what your solidified flux is, the slag, right? And that's all from this diagram, right? This explains the working process, right? So if you can understand what is happening here, you can write about submerged arc welding, right? It's that simple. You see here in 3D, as I said, it will be laid, right? That granular flux will be laid. So as we are moving from this to there, you see the travel direction from here to there. This is your weld metal, right? The fused flux shapes and protects the weld metal. As I said, just on top of the weld metal, you have the granular flux, which will protect the weld metal, right? Some of it will fuse also, right? It will join partially. And this will not join completely, as we have seen. That will be taken by the, what do you call, the vacuum system. That's what is happening here. You see that electrode is here, right? Heat of the arc melts the wire, flux, and plate, right? You have the wire, the flux, and the plate, right? So this is your working process in 3D, if you want to understand it better. Even another one I kept, right? This has more of, a lot of details, as you can see. Like for example, you have this welding wire here, right? Your flux, the flux hopper, right? Basically, this is what is responsible for feeding the flux, right? And what else do we have here which we did not have earlier? Work connection, that is basically that positive and negative, as we have seen. To generate the arc, the workpiece has to be what do you call, made as one terminal, and the electrode holder will be made as, I'm sorry, the electrode will be made as another terminal, just so that you have the affinity and the arc is generated, right? You see, this is where the contact is done for the terminal, right? The welding power would be supplied here to this electrode, and here you have it with the workpiece. So that's what creates the positive and negative, and that's what is responsible for the passage of current, right? What else do we have here? Bead of finished weld metal, right? And on the top you have the solid slab, right? The flux will stay on top of this, and flux shell, right? Basically, so that it doesn't distributes, okay? It doesn't disperses. You have this flux shell, just so you have flux maintained where it is required, right? Any doubts so far? Okay. So you see what we have discussed there is written here. The base metal is connected to negative energy source, whereas the electrode is connected to the positive source. In some devices, the granular flux is fixed with the electrode holder, right? That is also possible. The provision to have the granular flux fixed with the electrode holder, as we have seen here, right? It is fixed here, so you have that coming in, the granular flux coming in with the electrode itself, just by the side of it. Power is switched on and the electrode is brought near the base metal with the help of an electrode holder, right, where the weld is to be made. When it touches the base metal, the spark is produced, or the arc, technically, right? The arc is produced between them, and at the same time, granular flux is also provided, which shields the welded area, right? That's what we have discussed. Functions of the flux. Firstly, it shields the weld pool, right? That's the first function of it. It affects the weld metal chemistry also. Why? Because, as I said, some of the granular flux will be melted. It joins with the weld metal, the base metal, right? It joins with the base metal. So you have a composition which is mixed up of the weld metal, the base metal, and also the flux. So it affects the weld metal chemistry also, and therefore it affects the weld metal mechanical properties also, right? Because of that composition, you would have some kind of impurities or inclusions, if you want to call it, that alters the mechanical properties, right? So also affects the weld performance or characteristics, right? These are all derived of it, you can say, all derivatives, because of having those flux mixed with the base metal. Fluxes have variable burn-off rates, right? This is also another characteristics, that some have a higher rate of burning and some of them have a lower rate of burning, right? So the flux, the selection of flux depends on the material that you're trying to weld and the rate at which you are trying to do it, right? All these are factors to consider. Now you see the advantages. It has high deposition rate. Okay, you see here that is your flux, right? This is very clear here in this diagram, and that's where your weld has already been formed. So it has high deposition rates, right? This is one characteristic that is most commonly looked at when it comes to welding. What is the deposition rate? They want it to be higher, right? Generally, because that leads to lesser production time, and therefore it reduces the cost, right? The total manufacturing lead time will be reduced if you have a higher deposition rate. No arc, flash, or glare, right? Because of that, submerged is what we are calling it, right? Because that arc is now submerged in the flux. So no arc, flash, or glare, right? So that is what you call a sought after point, right? Both for the welder, it is good, and the surroundings, right? Minimal smoke and fumes. Because of that, flux and wire added separately. Extra dimension of control you have, right? Because they are added separately. So that control is there. Easily automated, right? This is possible to automate. Like unlike manual welding, arc welding is generally done manually. So not possible to automate that. Here it is easy to automate it, right? To be able to program it so that it can be done without, with reduced human assistance, right? Joints can be made with narrow grooves, right? You can see here, very narrow grooves. So you don't have much of preparation. Can be used to weld carbon steel, low alloy steel, stainless steels, chromium, molybdenum, right? Chromium, molybdenum steels, and nickel base alloy. These are the general metals which are welded with this method. Limitations: flux obstructs view of joint during welding, right? We are not able to see what is happening. So a completely transparent process. So that comes off as a limitation, that you're not able to see, you're not able to have a clear view of the joint when it is being welded. Flux is subject to contamination, porosity, right? Because that flux, if it is not melted properly, you will have porosity, right? Some air gap would be there, and that will affect the strength, right? Mechanical properties. Normally not suitable for thin material, right? And restricted to the flat position for grooves, flat and horizontal for fillets, right? That what do you call is also one restriction. That it has to be flat, isn't it? Because when this flux is poured on top of, as the electrode goes from here to there, the flux has to cover it, right? So it can only cover it when it is in the flat position, right? Flat or horizontal. If it is vertical, it would fall down. So that's why it is very difficult to do it vertically. That's why it is restricted to the flat position for grooves, flat and horizontal for fillets, right? Slag removal is required, right? You have to remove that slag, as I said. What vacuum was there, right? The vacuum system is responsible for taking the unused flux also, and slag also has to be removed. Flux handling equipment is also required. That is an additional equipment that is required, right? Applications you see. You have structural and vessel construction, as we have discussed, right? Most commonly carbon steels. Right? This is very relevant when it comes to civil engineering, right? Even pressure vessels. Electrical poles, wind turbine, pipes, surfacing applications, spear facing, build-up, corrosion resistant overlay of steel, right? So these are applications where the submerged arc welding is being used. And this is that video. Shall we watch the video? We'll have a better idea, right? And I've kept this additional information that it lays out the essential variables. Okay, what are the variables? For example, current, how current affects the penetration, increase of current or decrease of current, voltage, and the speed at which you are welding it, right? How these variables affect the depth of the weld, the width of the weld, right? All these things. So that is some additional information if anyone wants to look at.
Whiskas tasty mix. Real fish, chicken, veggies in gravy.
What can you get for rupees 99 today? Think, well, a bottle of cold drink?
Able to hear it? I think I've shared the sound also. Right? Able to hear, right? Okay.
Submerged arc welding. Submerged arc welding is a type of arc welding wherein the arc generated between the filler rod electrode and the workpiece is submerged within the pool of granular flux, which is excessively fed to protect the weld pool and arc zone from atmospheric contamination. The filler rod is fed continuously from a reel to the point of arc generation. And the flux is fed through a hopper, and the weld is advanced by either moving the workpiece or the system of welding itself. This video will cover the following about the submerged arc welding. 1. Working principle. 2. Equipment used. 3. Working. 4. Advantages. 5. Disadvantages. And 6. Applications. If you are new to this channel, click on the subscribe button and you can visit our website adtwlearn.com. Working principle. The working principle of submerged arc welding is similar to that of the shielded metal arc welding, wherein the arc is generated by striking the electrode against a workpiece or the area to be welded. The arc generated melts the filler rod, and the shielding is provided by the blanket of granular flux. Some of the flux which is closer to the arc melts and forms the layer of slag over the weld, thus protecting the weld. Equipment used. Power source. AC or DC with high current. Most submerged arc welding is carried out in direct current electrode positive, within the current range of 200 amp to 1200 amp. Electrode fed mechanism.
Right? The working principle is what I wanted to show. Right? You can watch the whole video. I've kept a lot of videos for your benefit, right? Because videos make the concept clear in a very short amount of time, right? Okay. So that was about submerged arc welding. Is that clear? Is there any doubts you can ask? Okay. You see, the next type of welding is the resistance welding. So, as the name suggests, it relies on resistance, right? We will see how that resistance is responsible for creation of that joint, right? It's a liquid state welding process, not actually a liquid. We can say it's a plastic state welding process. Okay, I'll explain that. Okay, it's a thermoelectric process. It uses electric resistance to generate heat, right? You have the concept of resistance, as I was saying, right? Electric resistance, that is what responsible for generating the heat. You see, basically, we want the generation of heat in any type of welding that you see. You have either the application of with the help of pressure or without the help of pressure, but there is heat required, right, for so that the metal or any other material that you are looking at is melted, right? So how do you generate the heat? The method that you use to generate the heat is what differs in different processes. So here we are using electrical resistance as a medium to generate that heat. Let's see how. And that's why we are calling it a thermoelectric process, right? You see, heat is generated by passing current through an electric resistance. As we know, this formula, right? Heat generated is given by the square of the current multiplied by the resistance or the resistivity of the material times the duration of it, right? And it also depends on these things: surface conditions, right? Current supplied, as we have seen, right? So you see, these are the types of welding. Okay, we'll understand the different types of resistance welding so that we can understand what is happening in resistance welding, right? These types, as we'll discuss, we'll get an idea of what is happening in resistance welding. So there are basically 4 types. We have spot welding, right? This is very what do you call, commonly used type of welding for automotive application, right? In automotive, I mean, be it a car or heavy machinery, okay, like I mean, heavy vehicles like trucks, buses, etc. Spot welds are required, okay, to join those sheet metal components. Spot welding is what is done. Okay, we'll see that in the next slides. Okay, hopefully. Seam welding, right? This is an extension of spot welding. Projection welding, and then you have flash spot welding. Okay, you see here spot welding. This is the simplest type of resistance welding. Okay, 2 copper electrodes with anvil faces. You see here, this is one electrode, and this is another electrode, right? With anvil faces. So basically, you will have that kind of sharp edge at the end. Okay, so they create a circular nugget. How? You see here, that's your nugget. What is happening is, just as you have the passage of current from one entity to the other in the arc welding process, here also these 2 electrodes, okay, they are charged, right? Current wants to pass from one electrode to the other, right? But because of the gap, why is there a gap? Because there is these welding plates in between these 2 electrodes. So the current is not allowed to move from this electrode to the other electrode. So because there is this gap, the current wants to jump from here to there, and because of this gap, there is resistance, right? These welding plates are offering resistance to the flow of current from one electrode to the other. And that resistance is what generates heat. And that heat is responsible for melting, it doesn't melt, okay? Technically, it doesn't melt. What it does, okay, what this resistance does is it generates heat. That heat is responsible for bringing the weld plates to the plastic state. Okay, it will bring it to the plastic state wherein basically it becomes soft. Okay, it doesn't melt. Melting is a different process altogether. Before melting, you have the softening, right? If you have seen blacksmithy on the roadside, what they do is they bring it to the red hot condition, right? That's what the plastic state I'm talking about. Right? So it doesn't melt, right? We know it doesn't flow when it is red hot, but it is soft, right? That is the state that we are trying to get here. Because of the heat that is generated, right? Because of the resistance, heat is generated. That heat will make the weld plates to turn into a plastic state, right? And that is when these electrodes, right, when it turns into plastic state, right, these electrodes will, because they are trying to create a pressure, right, they will force them to join, right? When it has turned in plastic stage, it has become soft, right? So because of that softening, you can easily join them together, right? These 2 plates, and when they are joined, you call this a nugget. Okay, we'll see the cross section of the nugget that will clarify what I'm talking about. But what is happening is you are trying to fuse them together, right? Very simple. Other type of welding, you see seam welding. Well, let me show you that cross section of the nugget. Okay, I think yes, it should be in the video. Okay, that nugget, what I'm talking about. You see seam welding, this is also known as continuous spot welding, right? As I told you, this is very similar to spot welding, but you have a continuous spot weld. The weld is continuous, so basically you are having multiple spots, right? So that's what makes it continuous spot welding, right? So a roller type electrode are used. You see, the electrodes here are roller types, right? Basically call them wheels. Create a continuous weld joint, right? The time and movement of electrode is controlled. How the speed of these rollers will determine the number of spot welds, right? And so the time and movement of electrode is controlled. Weld overlap and workpiece does not get too hot, right? It is used to create airtight joints, right? So if you want to have more strength, right, between the two weld plates, we'll go for seam welding and not spot welding. Because spot weld, they created at particular spots, so it doesn't have much strength, right? They can break as compared to your seam welded parts. Okay, this is also strong, but as compared to this, seam welding is more strong because you have multiple spots, right? Common sense. So this is used to create airtight joints, okay, because you are having multiple spots at very near distance, right? So this is basically one continuous weld we can call, right, as we are saying. So that's what this is for creating the airtight joints. Projection welding, you see a dimple is produced on the workpiece